In the last video, we built up a clear picture of what a routing table is, a structured list of network prefixes, each mapped to a next hop and an interface. A packet arrives. The router finds the best matching prefix, forwards accordingly. But we glossed over something. What happens when the routing table has more than one way to reach the same destination? And this isn't a rare edge case. In any real network, certainly at internet scale, there are almost always multiple paths between any 2 points. Redundant links, multiple providers, parallel connections. Redundancy is how networks stay reliable. Multiple paths are not an exception to normal routing. They're the norm. So when a packet arrives destined for a network that 2, 3, or 4 routing table entries could handle, each pointing to a different next hop, a different interface, potentially a different path across the network, how does the router decide which one to use? That decision is route selection, and it's more nuanced than it might first appear. The starting point is the longest prefix match rule from the last video. Before route selection even enters the picture, the router narrows the candidate entries by specificity. If one entry is a /24 and another is a /16, and both match the destination, the /24 wins automatically. No further comparison needed. Route selection only becomes relevant when 2 or more entries have the same prefix length, equally specific matches for the same destination. Now the router genuinely has a choice, multiple routes to the same place, and it has to pick one. The primary tool for making that choice is the metric. A metric is a number attached to a routing table entry that represents the cost or desirability of that route. Lower metric typically means more preferred. A route with a metric of 10 is preferred over a route with a metric of 100, assuming both reach the same destination with the same prefix length. But what does cost actually measure? This is where it gets interesting, because different routing protocols use completely different metrics, measuring completely different things. Hop count is the simplest metric and the oldest. It counts how many routers a packet has to pass through to reach the destination. A route that goes through 2 intermediate routers has a hop count of 2. One that goes through 5 has a hop count of 5. Lower is better. The routing protocol RIP, one of the earliest dynamic routing protocols, still encountered in some legacy networks, uses hop count exclusively. Hop count is simple to calculate and requires no knowledge of link speeds or conditions. But it has a serious flaw. It treats all hops as equal. A route through 2 routers connected by 10 gigabit links might be far faster than a route through 1 router connected by a slow satellite link. Hop count would prefer the second route because it has fewer hops. That's the wrong answer, and it's why hop count alone is considered a crude metric unsuitable for most modern networks. Bandwidth is a more sophisticated metric. It takes into account the capacity of the links along a path, preferring routes that run through higher capacity connections. OSPF, a widely used routing protocol in enterprise networks, can use a bandwidth-based metric called cost, where higher bandwidth links have lower costs. A gigabit link has a lower cost than a megabit link, so routes through fast links are preferred over routes through slow ones. Delay measures the time it takes for packets to travel a path, the latency. A route might have high bandwidth, but also high delay. A satellite link, for instance, has enormous latency due to the physical distance involved, even if its bandwidth is substantial. For real-time applications like voice or video, delay matters enormously. Routing protocols designed for these use cases incorporate delay into their metrics. Reliability tracks how often a link fails or drops packets. A link that works 99.999% of the time is more desirable than one that works 95% of the time, even if both have the same bandwidth and delay. Building reliability into a metric allows routing to naturally steer away from flaky connections, even before they fail completely. Some routing protocols combine multiple factors into a single composite metric. EIGRP, a protocol developed by Cisco, can incorporate bandwidth, delay, reliability, and load into one calculation, weighting them according to configurable parameters. This gives operators significant control over how routes are evaluated, but also introduces significant complexity. Now here's a layer of complexity that most introductory explanations skip, but that's essential for understanding real networks. Different routing protocols produce different routes, and a router might be running several routing protocols simultaneously. Imagine a router that has learned a route to 10.1.0.0/24 from 3 different sources: a static route configured manually, a route learned from OSPF running inside the organization's network, and a route learned from BGP, the protocol used between organizations on the internet. Each of these sources has different metrics in different units. OSPF costs are measured one way. BGP uses a completely different set of attributes. Static routes have no metric at all. Comparing an OSPF cost of 20 to a BGP metric is like comparing kilometers to degrees Fahrenheit. The numbers are meaningless relative to each other. So before metrics are even compared, routers apply a higher-level preference called administrative distance, a number that ranks the trustworthiness and preference of the route's source. Lower administrative distance means more preferred. Static routes typically have a very low administrative distance. They're manually configured by a human who presumably knew what they were doing, so the router trusts them highly. OSPF routes have a moderate administrative distance. BGP routes, especially those learned from external neighbors, have a higher administrative distance, reflecting that they come from outside the router's own network and carry a degree of inherent uncertainty. So when a router has routes to the same destination from multiple sources, administrative distance is the first tiebreaker. Only if 2 routes have the same administrative distance, meaning they came from the same protocol, does the router move on to comparing their metrics. Administrative distance first. Metric second. Prefix length first of all. That's the hierarchy of route selection. But even technical metrics and administrative distance don't tell the whole story. In the real world, routing decisions are often driven by factors that have nothing to do with network performance at all. Consider an organization with 2 internet providers, a primary ISP they use for most traffic, and a backup ISP they only want to use when the primary fails. Technically, both provide equivalent connectivity. The backup provider's routes might even have better metrics on some paths, but the organization has a policy: use the primary, always, unless it's down. That policy has to be expressed in the routing system somehow. Or consider an ISP that has a paid peering relationship with another network, meaning they pay for traffic that flows between them. They also have a settlement-free peering relationship with a third network, meaning traffic flows between them at no cost. Everything else being equal, the ISP wants to route traffic through the free peering relationship rather than the paid one. That preference isn't a technical metric. It's a business decision, expressed as a routing policy. This is called policy routing, the use of routing configuration to steer traffic based on criteria beyond pure technical performance. It's pervasive in real networks, and it becomes especially prominent in BGP, the protocol that governs routing between different organizations on the internet. BGP is at its core as much a policy system as a technical routing system. Its attributes and configuration options exist largely to let network operators express business relationships and traffic preferences as routing decisions. Policy routing is where networking meets economics and politics. The Internet's routing system isn't just optimizing for speed and reliability. It's reflecting commercial agreements, regulatory requirements, and organizational preferences, all encoded as routing policies that shape which paths packets actually take. One more concept worth understanding before we close. What happens when the router has genuinely equally good routes to the same destination? Same prefix length, same administrative distance, same metric. In many routing protocols and router implementations, the answer is use all of them. This is called equal cost multipath routing, or ECMP. Instead of arbitrarily picking one path and ignoring the others, the router distributes traffic across all equal cost paths simultaneously. Packets flowing to the same destination might take different physical routes through the network, one going left at this junction, the next going right. The load is spread. The total capacity available to that destination is the sum of all equal cost paths rather than just one. ECMP is widely used in data centers, where traffic between servers often has multiple equal cost paths through a network of switches and routers. It's also used in internet backbone networks, where parallel high-capacity links run between major interconnection points. Rather than treating redundant paths as failover options, used only when the primary fails, ECMP treats them as active resources, all carrying traffic simultaneously. The practical detail of how packets are distributed across ECMP paths matters more than it might seem. You generally can't just round-robin individual packets across different paths. Packets belonging to the same connection might arrive out of order if they take different routes, which breaks TCP badly. Instead, routers typically hash on the combination of source address, destination address, and port number, so all packets belonging to the same flow take the same path, while different flows are spread across different paths. The load balancing operates at the flow level, not the packet level. Consistent for each connection, distributed across connections. So let's assemble the full picture of how a router selects a route. First, the longest prefix match narrows candidates to the most specific entries. Then administrative distance ranks them by source trustworthiness, eliminating routes from less preferred sources. Then metrics compare the remaining candidates within the same protocol, selecting the lowest cost path. Policy overrides can intervene at any stage, steering traffic based on operator-defined rules regardless of what the technical metrics say. And when multiple routes are genuinely equivalent across all these criteria, ECMP puts them all to work simultaneously. Route selection isn't one decision. It's a hierarchy of decisions, each one narrowing the field, with policy able to influence the outcome at every level.